Welcome, everyone. Today, we're diving into the fascinating world of number theory as we explore how to compute the GCD sum S of n using divisor grouping. Last time we saw that a messy sum of greatest common divisors in one variable can sometimes be rewritten as a neat divisor formula. Here is the definition of S of n. For a fixed n, we add the greatest common divisor of k and n as k runs from 1 up to n.
So even for something like n equals 12, that would already be 12 different greatest common divisor values to add up.
We lock in one integer n and study how all the numbers from 1 to n interact with it.
That means the sum could have a lot of pieces if n is large.
Exactly. Which is why we want to look for a pattern instead of computing every greatest common divisor directly. Our aim is to compress this long sum into a shorter expression that talks only about the divisors of n and the totient function. To do that, we will group together all k that share the same greatest common divisor with n and see how many are in each group. Now we reorganize the sum by looking at all numbers k that share the same greatest common divisor with n. Start by focusing on one particular divisor d of n and collect all terms whose greatest common divisor with n is exactly that, d.
If the greatest common divisor of k and n is d, that means k must be a multiple of d, right?
Yes, we can write k as d times some integer t, and every k in this group has that form. When we divide both k and n by d, the new pair t and n over d must be relatively prime. Otherwise, the greatest common divisor would have been larger than d. The number of t between 1 and n over d that are relatively prime to n over d is exactly the totient of n over d.
So each divisor d contributes d times phi of n over d to the big sum.
Putting all the groups together, S of n becomes a sum over all divisors d, where each term is d times phi of n over d.
So we have turned a long sum over k into a shorter, more structured sum over the divisors of n.
Later, you may see this written as a Dirichlet convolution. But the key story is just grouping by the greatest common divisor and counting with the totient function. Let us test our formula on n equals 12, so we can see the grouping in action with concrete numbers. First list the divisors of 12, since those are the only possible greatest common divisors with 12.
Then for each divisor d, we look at numbers whose greatest common divisor with 12 is that d, and they are counted by phi of 12 over d.
Right? And each of those numbers contributes d to the sum, so the total from that group is d times phi of 12 over d. Finally, we just add up all those group contributions to find S of 12. Using the formula, we plug in each divisor of 12, compute the corresponding phi values, and multiply to get each group contribution.
The numbers add up to 40, so S of 12 equals 40 using the divisor-sum formula.
If you list all the greatest common divisors of k and 12 for k from 1 to 12 and add them directly, you also get 40, which confirms the formula matches brute force. Before we finish, try one more GCD sum and think about where this trick might show up again. Take a moment to think how you would use the divisor formula to find S of 8.
I would list the divisors 1, 2, 4, and 8, then use phi of 8 over d and multiply by d for each one.
Using the formula, S of 8 is the sum over divisors d of 8 of d times phi of 8 over d, which gives contributions of 4, 4, 4, and 8.
Those add up to 20, and if we check by listing the greatest common divisors of k and 8 for k from 1 to 8, we also get 20.
As a quick check, you can compute each greatest common divisor with 8 directly and confirm that their sum really is 20.
So the function S of n behaves like a product of the identity function and the totient function under this special Dirichlet convolution operation.
Exactly. And many other sums built from greatest common divisors or divisors of n can be understood in the same way by grouping and counting. Keep this grouping trick in mind whenever you see a sum that depends on the greatest common divisor with a fixed number. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.